Good afternoon and welcome to CON206. Accelerate your Kubernetes journey with Amazon EKS. In this session, you'll hear about the major concerns of customers running Kubernetes workloads in production. Concerns like managing the control plane, scaling the cluster, and let's not forget about upgrades. You'll also hear how Amazon EKS was built to address those concerns and provide you with production-grade Kubernetes. We'll also provide an insight into some EKS best practices that come from working with our customers. Right at the end, we'll finish with an exciting announcement that will give you an opportunity to be amongst the first people in the world to unlock a new achievement. My name is Liz Duke, and I'm a Principal Specialist SA for Containers at AWS. And I'll be joined on stage by Pratik Gogia, who's a Senior Software Engineer in our Kubernetes team. I wanted to start off by talking about the impact that Kubernetes has had on container orchestration. It's huge. Kubernetes is open source, and it's a graduated project from the CNCF, or Cloud Native Computing Foundation. I don't know if you've seen all the projects the CNCF has. It's a little like this. Yeah, I know, we can't talk, right? This is a slide from a couple of years ago, as I can't fit all the services on one slide these days. So with all of this choice, it can be hard to know where to start. EKS simplifies a lot of those options for you. Not that you couldn't include these projects, or maybe just a few of them if you wanted to, as EKS is upstream Kubernetes conformant, but EKS comes with pre-built options for things like logging, the container network interface, and ingress. EKS also provides you with supported Kubernetes versions that have been battle-tested for security and scalability. Now, from listening to our customers, we hear some common themes as to why customers are moving to containers. They want to move quickly to keep up with the pace of innovation in technology. And microservices help you do that by enabling individual teams to work on specific features. But even when moving quickly, though, they don't want to be insecure, so security is paramount. But it's no good having a secure solution with lots of features if it doesn't scale and it's not performant, because your customers will go elsewhere. In today's economy, it's more important than ever to only pay for what you need when you need it. If you need to expand to serve customers in another geographical region, you want to be able to create that solution quickly without blowing the budget. Now, more than ever, organizations are looking to modernize legacy systems, and increasingly they're looking to do that on AWS with Kubernetes. This in turn brings its own challenges, especially around matching that Kubernetes release cadence with the additional governance that comes with being an enterprise organization. Of course, you want that Kubernetes agility and pace of innovation. So how can EKS help you align that speed with your processes and make it easier for you to not only know the impact of upgrading, but how to improve and de-risk that upgrade experience? Let's see. So what makes up an EKS cluster? Well, an EKS cluster is a Kubernetes cluster. And some of you may be very familiar with Kubernetes and others less so. A Kubernetes cluster is a way to run containers in units called pods. And it consists of two main areas. You have the control plane, which is used for running the cluster, and you have the data plane, which is used for running the applications themselves inside of pods. EKS started with a managed control plane, as that's the part that customers told us that they had the most problems with. upgrades being a particular pain point, but also scaling it and making it resilient. So how does EKS help with that? Well, the control plane for EKS is fully managed and resilient. We run 2 copies of the API server and 3 copies of etcd, the Kubernetes state store, in an AWS managed account across multiple availability zones. The control plane of EKS is designed to withstand single availability zone events. And of course, you also get AWS support with your EKS clusters. As for upgrades of the control plane, you've got to keep on top of these, as Kubernetes has 3 releases per year. Now with EKS, these upgrades are just a single action, either through the console, the API, the CLI, or through our preferred command line tool, EKS Cuddle. And we support 4 current versions of Kubernetes. When you're running Kubernetes clusters, you want to be able to scale your cluster easily. And when you scale your pods and nodes, EKS takes care of scaling the control plane for you behind the scenes. As we learned how the control plane behaved under different conditions, we adjusted our metrics to make that scaling more responsive. Now we use a variety of metrics to scale the control plane, including the number of worker nodes and the size of the etcd database. And once we've scaled up the control plane, we won't scale it back down again unless your utilization has dropped below that scaling threshold and remained there for several days. Security comes built in with the EKS control plane. We apply security patching, including embargoed CVEs, those are common vulnerabilities and exposures. We encrypt the etcd database, and we secure access to the control plane. As I said, EKS supports 4 Kubernetes versions at any given time, which gives you up to 14 months to upgrade, although we'd really like it if you'd upgrade a bit more often than that. We don't allow alpha feature flags, as we don't trust that in most cases that they're stable enough for use in production. But what about user access to the cluster itself? Kubernetes doesn't actually come with a user directory. It expects you to provide one while it gets on with its core task of orchestrating the pods. We do have a service that deals with managing users. You might have heard of it, IAM, or Identity and Access Management. That service scales rather well, and so we integrated it as the user authentication service to the cluster. And the way we did this was to use a Kubernetes object called a config map. Now this is a YAML config file, and the feedback we got from our customers was that they didn't really enjoy this method of integration. And so, coming soon, we have IAM Cluster Access Management. Because up until now, what you would do is you'd create the cluster using the EKS APIs, and then you'd switch to using the Kubernetes APIs to manage user access. Now with Cluster Access Management, you'll be able to control both your user authentication and authorization using one set of APIs and no more awkward YAML config file. Other AWS services integrated with EKS, like Amazon Elastic MapReduce, can also use Cluster Access Management controls to obtain the permissions they need to run applications on EKS clusters without the need for cluster admins to perform multiple prerequisite configuration steps. Now, as I said earlier, Kubernetes releases a new version 3 times a year, and EKS supports 4 versions at any one time. So to work with Kubernetes, you've got to be working with the release cycle. And we see customers wanting more help in this area. So one of the areas that the service team have worked on has been the upgrade time of the control plane. Now, as I said, upgrading the control plane is a single action, but previously it could take up to around 40 minutes once you'd kicked off that upgrade for it to complete. Now, it should complete in under 10 minutes. Customers really like that upgrade experience with a single action. So on our roadmap, we've extended that ability to not only upgrade the control plane, but to also upgrade the data plane and add-ons. Where customers also need more help is with the ability to upgrade with confidence. So if you have multiple teams running on top of the same EKS cluster, you might not know all the APIs that they're calling. And between Kubernetes versions, you get APIs that come in, you get APIs that are deprecated. So to help with that on our roadmap, you will be able to generate a report on the readiness of your cluster to upgrade to the next version. And along with these features will come a metadata API. So you'll be able to run these actions programmatically. Now with Kubernetes, the support lifecycle comes from the Kubernetes project. And that's why EKS follows that same lifecycle. At the start of this talk, I mentioned that we supported each Kubernetes version for 14 months. But we know that keeping up with that Kubernetes release cycle is difficult, especially for those customers who might be reliant on third parties testing their applications against new versions of Kubernetes, or maybe, in your case, you have to have extended change freeze windows over maybe the end of an extended financial year for reporting purposes, or over holiday periods. We've just had Thanksgiving in the US, we're coming up to Christmas. Maybe you need an extended change freeze period that covers from before Thanksgiving into the new year. Now you can focus on your business requirements and upgrade when it's convenient for you. Because earlier on this year, we announced extended support for Amazon EKS in preview. This extends that 14-month upgrade period out to 26 months, and best of all, there's no action needed by you to enroll in this. As long as you're on version 123 or higher, when your version goes out of normal lifecycle support, you'll still be supported. I've spoken a lot so far about the control plane, but what about the data plane? You've got different options with the data plane for EKS, but again, where customers were telling us that they needed help was in upgrading it and in scaling it. So how does EKS help with that? Let's first look at the different options you've got for the data plane. The original option for the data plane was self-managed EC2 instances, and that's still available today. With these self-managed instances, you're fully in charge of controlling the lifecycle of those instances. You provision them, they exist in your accounts, and you make sure that you upgrade your nodes and you manage the lifecycle of those instances while you're doing that. You also have to be aware that you need to upgrade your AMIs underneath when there's security releases. With EKS managed node groups, which is another option, we step in and take some of that responsibility away from you. We help you both in provisioning the nodes, in scaling them, and in handling them during the upgrade process. And then we've got Carpenter. Carpenter's the new kid on the block. It's an open source autoscaler that works with your EKS clusters to provision the right nodes for your workloads. Our final option is AWS Fargate. With Fargate, you specify the amount of CPU and memory you require, and that's what we bill you for. So you get that granularity of billing down to the pod level. So looking at managed node groups a little bit more. Managed node groups for EKS come with autoscaling groups, which configure the EC2 instances on launch. And managed node groups simplify the worker node upgrades by managing the cordoning and the draining of the nodes, and also by scaling the number of nodes in your autoscaling groups so you don't suffer from reduced capacity during that upgrade process. Now, this used to be done on a node-by-node basis, but we've got customers with a large number of nodes in their node group, so this really didn't work for them. And so we extended this to make it possible for you to upgrade nodes in parallel. So now you can select either a percentage of nodes to upgrade at the same time, or a specific number of nodes to upgrade at the same time. And when there's a new AMI available for your managed node group, you'll be notified. So why am I calling Carpenter Intelligent Compute for Kubernetes? Well, when you want more copies of your application running in more pods, then you need more instances. And normally this works in Kubernetes by integrating with the cluster autoscaler. The cluster autoscaler then talks to the EC2 autoscaling group and say, I need more instances. These nodes would then join the cluster, and the pods which have been in pending status get scheduled on the nodes. But there's always been a disconnect between the autoscaling groups and the EKS cluster, because the autoscaling group doesn't know or care about the cluster. All it knows is that it's been told more instances are needed. Autoscaling groups are also seen as being more restrictive in what nodes can be part of an autoscaling group, and diversifying the autoscaling group is also seen as a pain point by customers. So the EKS service team created Carpenter. This interfaces directly to the EC2 Fleet API, and it selects the most optimal nodes based on what's in your pod specification. So say, for example, your application needs to run on GPUs instead of CPUs, and you put that in your pod specification. Carpenter will go out and find a node that suits. Carpenter also looks to see how it can pack pods onto nodes, doing bin packing on your behalf. Carpenter also will consolidate pods onto smaller nodes if the demand on your application reduces and your nodes and your pods scale in. Today, we have many customers running Carpenter in production, seeing not only great performance, but also awesome optimization, leading to impressive cost savings across their clusters. Now, if you don't want to manage compute at all, not even the tiniest bit, you could use our serverless offering of EKS Fargate. With Fargate, we manage the patching, the updating, and the scaling of the underlying nodes. And we don't share those underlying nodes with other pods, whether it's for another customer or within the same account. There are some considerations, as you can see from the slide, but with Fargate, you get to truly focus on spending time on your business applications rather than managing infrastructure. We implement the EKS VPC CNI container network interface by default when you build an EKS cluster. The VPC CNI takes care of requesting a new VPC IP address for every pod that's created. Now, in Kubernetes, by default, every pod can talk to every other pod. So to restrict traffic between pods the Kubernetes native way, you'd implement network policies. Previously, customers would have to add in an additional third-party CNI to implement network policies in their EKS cluster. And this was more work both to manage and to keep updated. So the support for network policies built into the VPC CNI was one of the most requested features on our roadmap. And earlier on this year, we released that feature. We implemented the feature using eBPF, which has a lot of advantages over more traditional methods such as IP tables. Some of these advantages are things like more efficient packet filtering, which can lead to better performance. Using network policies, you can implement granular network restrictions between pods and implement least privilege at the pod level. This adds to your defense in depth strategy for EKS. Now, Kubernetes clusters rarely exist in isolation. They're part of a workload environment. Maybe your application requires a message queue like Amazon SQS, and most likely you'll be integrating against one or more databases like Amazon DynamoDB or Amazon RDS. So you need to think about the security of integrating to those other AWS services. I already mentioned using IAM for user access and network policies to restrict network traffic. But what about using IAM roles to restrict access to other AWS services. With EKS, you can do that as well. And what about sensitive information like passwords? Kubernetes stores sensitive information, just like other container orchestrators, in objects called secrets. These are stored in etcd. Now, by default in Kubernetes, these are only base64 encoded. But with EKS, you not only get encryption of etcd by default, which protects your secrets where they're stored, but you can also use KMS envelope encryption, which protects your secrets where they're used. And maybe you want to run analytics workloads on EKS. Using Amazon Elastic MapReduce on EKS, you can use a single EKS cluster to run multiple Apache Spark versions and configurations, along with automated provisioning, scaling, and faster runtimes. Another higher-level service like EMR that's integrated directly with EKS is Amazon GuardDuty. Amazon GuardDuty is a managed threat detection service that provides you with a more accurate and easy way to continuously monitor and protect your AWS accounts and workloads. You've been able to monitor the EKS API actions using AWS CloudTrail and have access to the Kubernetes audit logs for a long time now. Now you can continuously monitor all your Amazon EKS clusters across your organization with just a few steps in the GuardDuty console. And you can protect your EKS workloads with a new GuardDuty security agent that adds visibility into individual container runtime activities. Using Amazon GuardDuty EKS runtime protection adds a layer of security with very little work required by you to implement. You can enable it with just 2 steps. The first step enables GuardDuty runtime monitoring for EKS in your account. And the second step deploys the agent across your clusters. Now, GuardDuty starts looking for unusual and suspicious behavior. So maybe your pods are trying to contact the IPs of known command and control servers to make them part of a botnet. Or maybe they're trying to look at the host metadata to gain access to IAM credentials. You can then make informed decisions based on those findings. You've probably got at least one operations team, and maybe more. So to make it easy for centralized operations teams to know about your Kubernetes clusters, Amazon EKS has a console that can be used to see all of your Kubernetes clusters, whether they are other EKS clusters, other Kubernetes clusters running on AWS, on-premises, or even on other clouds. It does this using the EKS connector. There's always been a tension between making sure your workloads operate at the right sort of level of performance and give you the right availability, and balancing that against the cost to run those workloads. This can be more of a challenge when we're looking at doing this in Kubernetes, because you could have multiple teams running on the same underlying cluster, so you need to be allocating the costs to those teams accurately. Or maybe you're actually running a multi-tenant cluster for your customers, and you need to charge those customers the right amount for the resources they're using. So you're doing chargeback or showback, and most likely you want to be doing reporting, budget forecasting, cost optimization. There was a study that was done by the FinOps Foundation that found that when they did this study and surveyed customers, less than 66% of organizations had any form of detailed Kubernetes cost monitoring. And only 22% of the organizations who were surveyed could accurately predict their Kubernetes costs to within 5% or better. So what drives these costs? What their survey found out, and what we see, is that the majority of costs for your Kubernetes clusters, and no different on EKS to other Kubernetes clusters, comes from your compute and memory. It's over 90% of your overall costs. Yes, you might have other costs that come from, for example, running third-party applications on your cluster, so you might be paying license fees for those. Maybe you've got some storage if you've got stateful workloads, or maybe you're sending data across availability zones and you've got some data transfer costs. In fact, the cost for the managed control plane is almost insignificant compared to these other costs. And if these costs are coming from applications which have been specified incorrectly for how much CPU and memory they need, then what we see is a lot of underutilized resources. Because you know what it's like, right? You ask somebody, how much CPU and memory do you need to run this application? And more than likely, the first initial estimate is a finger in the air, this is how much I need. Which is fine as long as you're continually measuring that and adjusting that based on the performance of the applications. Otherwise, the scheduler just looks at how much you've specified for that pod and looks to find the available amount of resource within your cluster. And if you're using an autoscaler and that resource doesn't exist, it'll spin up more resource to host that pod. So you need to be aware of what you're spending on your pods. So when you're looking to optimize costs, you not only need to measure the performance of your applications inside your pods, but how much those are costing you, whether it's at the pod level or more commonly at the namespace level. A lot of customers have been using KubeCost for this. Now, originally KubeCost came in two different flavors. You had the open source version, which came with a limited feature set, support from the community, but was free. And then you had the enterprise version, which was supported directly by KubeCost, came with a richer feature set, but came with an enterprise license cost. With EKS, you've got a third option, and that's the EKS Optimized KubeCost bundle. We've partnered with KubeCost to give you a version of KubeCost with more features than the open source version. You get support direct from AWS with this version of KubeCost, but you don't get charged for it. We pick up the licensing fee for that. You can deploy this version of KubeCost onto your EKS clusters either by using a Helm chart, by using a managed add-on, or from the marketplace as an add-on from the marketplace itself. And you can also now get a unified view across your clusters for the costs that you're incurring by using this optimized KubeCost bundle. So whether you take advantage of the depth and breadth of services that AWS offers to build new cloud-native applications, or you want to use third-party software applications on your EKS clusters, AWS can help. The AWS Marketplace and Amazon EKS have partnered to give customers a better experience. You can deploy software solutions from providers as an add-on. Some of the available options are Crossplane from Upbound, Apache Kafka from KPow, or Dynatrace from Dynatrace. So you might be thinking, all this is great if I want to run Kubernetes in the cloud. But what about when I need it in a particular country because of data residency requirements? Or maybe you've just invested a lot of money in your on-premises infrastructure and you'd like to make use of it before you retire it. We have as a goal to provide our customers Kubernetes how they want it, where they need it. This includes in the cloud, on-premises, and everywhere in between. So hopefully you can see why Amazon EKS offers you production-grade Kubernetes and how we're always focusing on continually improving the service to better enable our customers. With that, I'd like to hand over to Prateek, who's going to cover some common issues and best practices to help you get up and running quickly with EKS.
Thanks, Liz, and hi, everyone. Now that we have explored the EKS architecture and the options to run Kubernetes with AWS, I would like to share some of the best practices that EKS recommends based on managing hundreds of thousands of Kubernetes clusters across the globe and helping customers run their critical production workloads on these clusters. Let's take a look. Let's start with a scenario. You're starting to take digital orders for your coffee shop and need to deploy an application that can take these coffee orders. For this, you have created an EKS cluster, added a node to this cluster, and now you deploy your application, which is running on this node 1 in the availability zone 1. Considering this pod is running your critical business application, is deployed in this availability zone 1 and is now serving your customers. Now, if for any reason node 1 needs a restart or an upgrade, it can cause a downtime. And in the business, you don't want that to lose orders. So it is recommended to run multiple replicas of your pod, avoid running singleton pods, and use topology spread to run these replicas across different nodes in different availability zones. Now that you have a stable application running and we are able to serve our customers, take some orders, you see an increase in demand in these digital orders and need to handle large number of requests for which you need to scale your application. To be able to better auto-scale your application, consider using horizontal pod autoscaler or use vertical pod autoscaler, which can help you manage number of pods required to be able to serve the current demand when there are large orders coming in and scale down at night when people are not ordering coffee anymore. Now, as the pods are being auto-scaled, you also need to ensure that there are nodes available where these pods can run and scale down these nodes when the demand reduces. You would definitely want this to be seamless and fast without customers noting this. It is recommended to configure and run a node autoscaler, either Carpenter or cluster autoscaler, for managing your nodes for this purpose. EKS team developed Carpenter, as we saw in earlier slides, to help users to save infra costs and have efficient resource utilization to help with such scenarios. Everything is great. You have your application auto-scaling in and out, saving you hundreds of thousands of dollars in infra and operation costs when not required, and you're able to serve your customers best. However, suddenly you see some of the pods are not running or serving any customer request anymore. Let's first see, as an EKS user, what tools are available and how you can use these tools to diagnose such scenarios. Starting with, you would want to monitor any errors that are happening in your cluster or just how your cluster is performing with your control plane to check how are requests being processed by the API server running in your control plane. Next, you would want to monitor all the nodes that are running if they're running into any kind of issues, or any other critical components like storage or networking to check if there are any network-related issues that might be causing such issues in the cluster. You start with your metrics and logs from all these components and start to analyze them. But how do you proceed? Like, which tools do you use to start looking for these metrics and logs? Let's see what are the tools available at your disposal. To make it easy for you to collect and visualize all the cluster insights, EKS provides all the logs and metrics from control plane and data plane in your CloudWatch in your account. Users can run CloudWatch Insights queries to analyze Kubernetes control plane and check how the requests are handled by control plane. Similarly, they can run these insights and that can help you scrape metrics from your workload related to resource utilization on the nodes, pods, network performance, status of your nodes. CloudWatch also allows you to have pre-built dashboards for metrics, giving you a single pane of glass for all your metrics. Also, you can publish all these metrics to Amazon Managed Prometheus through the agentless feature, which was just announced a couple of days ago. Next up is logging. You can configure your cluster to publish all the control plane and data plane logs to your CloudWatch accounts. For data plane, you would need to install a daemon set, something like FluentBit, and once all the logs are published to CloudWatch, Container Insights classifies these logs into 3 different categories by default. Starting with your application logs, these are directly streamed into your application log groups. Next are your host logs. These are things like var log messages, which go into your host log per node. And then the last category is your data plane logs. These are for components like kube proxy, AWS node, or container runtime, which is running on every worker node and are responsible for maintaining running pods and are captured as data plane logs. Great. Now that you have monitoring for your metrics and logging established for your cluster, and with the help of these tools and data that you are collecting, let's see how we can narrow down why are the pods not running in that cluster that we started. Let's start with checking what's happening in the control plane, where you can check your API server metrics and API server audit logs. Starting with the metrics. You can check if your API server is healthy and available, there are no delays from the API server, and there are no errors for the requests that are being sent to the API server. So in terms of API server metrics, everything looks good. Let's continue looking at the audit logs, which will help us answer some deep insights into API server operation for things like, are there any errors returned for requests sent specifically by your user agent? Are there any errors for requests being sent by the core controllers, such as running in Kube Controller Manager? Are there any errors during scheduling these pods from Kube Scheduler? These are just some examples for things you can find answers based on your metrics and logs by using the container insights. EKS team also publishes a sample sample insights queries in the link pasted here in the AWS observability guide under log aggregation. Continuing our search for the answer for why pods are not becoming ready, let's analyze the data plane metrics and logs for the kube nodes. Again, CloudWatch Container Insights to the rescue, and we are able to answer things like, are all my kube nodes healthy? Are kube nodes running into any kind of resource limit like CPU or memory pressure? Looking into the data plane logs, you check if the container images for all the pods are available on the nodes. Dependent objects like secrets and config maps are available. And are the nodes running into any kind of IP exhaustion? And looks like in this case, that's what's happening. We have a node running out of free IPs, which is causing pods to not go into the ready state. Let's see if this info is available somewhere else as well. Enter the world of cluster networking. As pods are created and terminated in the clusters, IPs are assigned and they become available. Before looking into the metrics available from cluster networking, for those who are not familiar with cluster networking, let's understand at a high level what it means. A cluster network, more commonly also known as CNI plugin, can be used to configure pod networking in a Kubernetes cluster. EKS does come configured with its networking out of the box, which is AWS VPC CNI, and it uses AWS IPAM to assign the IP addresses. That means you get native VPC networking. This also means you get simple, secure networking, which is inbuilt, and you can use tools like VPC flow logs to monitor the traffic. EKS team provides a CNI metric helper tool to scrape this information. It aggregates metrics on a cluster level and publishes all the metrics to CloudWatch. There are a large number of metrics published by this tool, but there are some sample metrics which can help you answer things like, how many ENIs are available or allocated in my VPC and cluster? How many IPs are available or used in your VPC? Now, this provides you with an option to configure alarms to avoid running into a situation, and users can take proactive steps by adding secondary siders or using IPv6 address types for your clusters. Let's see why does monitoring the ENI and the IP usage for the subnet used for the clusters becomes very critical. As we saw in an earlier slide about the EKS architecture, the communication between the customer VPC and the control plane is also established through an EKS managed ENI. If your account is hitting any of these limits for ENI creation or IP exhaustion and new ENIs cannot be created or no free IPs are available. This would mean upgrades like scaling and security-related patching to your clusters are blocked and clusters are marked as degraded. As you start running large number of critical applications in these clusters, it becomes critical for the control plane of these clusters to be scaled and upgraded whenever required. Let's take a look at another scenario in your cluster. As the usage of your cluster increases, there are more and more developers and operators who are deploying their applications on these clusters, and you need to ensure they're labeling their pods correctly. For that, you consider adding admission controller webhook to your cluster. Let's take a look at a high level, how does this work with your requirements? You have a user who is talking with your API server. This could be your end user or CI/CD, and they send a request to create pods. When the request is being sent to create pods, API server forwards it to the admission webhook controller. It verifies that the pod spec contains the label. Once everything is correct, it returns back the response to API server, and your pod object is created in etcd. You might already be running various webhooks in your cluster for different use cases. So let's take a look at how you can ensure these webhooks are not impacting any of your requests in API server. EKS Kubernetes control plane provide metrics for API server, which can help you monitor in case API server is not able to reach the admission webhook controller. Similarly, you should also be monitoring in the case admission webhook controller is responding with any errors for the requests that are being sent by API server. For scenarios where possible, you should also configure admission webhooks with a fail open policy shorter than 30 seconds, which prevents requests from being completely rejected from the API server. Kubernetes docs actually provide some more best practices around when running admission webhooks in production. What are some of the additional things you should be considering? I do recommend checking those docs out. All right. Now that you're not a small coffee shop anymore, taking hundreds of orders every hour and serving other items as well, as a result, your cluster has increased. And as a result of this, there are a large number of requests being sent to the API server. And occasionally, you see errors like 429 when interacting with control plane. Before we see what's the most common cause and how to mitigate these errors in API server, let's first understand how does API server handles these requests. Prior to API priority and fairness, which is a new feature which got added in Kubernetes 120, any kind of call like a health check request, any call from kubelet, get or list requests were all treated equally at the API server level. API server did provide a couple of flags to control how many mutating and non-mutating requests can be in flight, and the remaining calls would get denied with a 429 status code. What this meant was if there are large number of heavy calls being made, which are represented here in red, for example, these are list calls which are listing hundreds of thousands of objects in your cluster, it could potentially impact the static stability of your control plane, since other health check requests could be rejected while API server is still processing these large time-consuming requests. So how does AP&F help in this case? It introduces two resources. First is the priority level configurations, and the second one are the flow schemas. Priority level configurations define the priority levels for your requests, and the flow schema help classify each request and match them to a priority level. In simple terms, we can think of these as requests that get added to separate queues. With this now, health check and other critical calls for static stability can be in their own queue and not be impacted in case there are other slow and large requests being made in the cluster. However, if you have APF configured with critical calls like create pod calls for your application, and there are list calls which are also using the same bucket, it can potentially impact your create pod calls because they are all falling into the same bucket. At this point, it becomes really critical to monitor control plane metrics for APF that can help you diagnose this much earlier in case you are hitting any concurrency limits or queues are getting filled up. Also, it is recommended to reduce the large number of expensive list calls being made to the control plane. Shout out to the EKS scalability team as they have published a great documentation in EKS best practices guide in this link, where they go over these best practices around APF, which metrics to monitor, and some more background around APF. Finally, I would like to summarize some of the learnings and the best practices when running EKS clusters. Run pods as part of your deployments and use topology spread. Configure pods and node autoscalers. Monitor metrics and logs for your control plane and data plane. Use CNI metrics helper for monitoring CNI metrics or any other component that you are deploying, which are critical to your application. Make sure you monitor your admission controller webhooks, configure APF flows for critical requests, and monitor APF metrics. This was just a set of most recommended best practices which can help ease a large part of your operations. EKS team publishes a complete guide for best practices which is quite comprehensive and covers topics like security, scalability, reliability, and networking. I would highly recommend checking this link in case you haven't seen this. Next, over to you, Liz, for the final announcement.
Thanks, Prateek. So finally, we're at the end of our talk, and I did say that we provide you with the opportunity to be amongst the first people to unlock a new achievement. Now, until now, we haven't had any specific EKS digital certifications, so I'd like to tell you about the first one of its kind. We're launching the digital EKS learning badge along with its learning path. In fact, it went live just the other day. So if you or your team want to know about the core concepts of EKS and how to get started, we've got you covered. You'll also be able to take an assessment and earn a digital badge that you can then share on your resume with your employer or on social media. Test your level of knowledge on Amazon EKS and show what you know. Thanks for attending the talk. I know it's at the end of a long day.